looks like we're starting to get more people filtering in. So we're going to go ahead and get started with our webinar for today. Thank you so much for joining us. My name is Julia, and I am in NRL Communications, and I am handling the technical aspect of today's webinar. So before we get started, I am going to go ahead and go over a few housekeeping rules for the webinar. Okay, so a couple things to note. Everybody is muted today, and you have two options for audio. You can either use your computer audio or your phone audio. So if your computer audio doesn't seem to be working, you can always navigate to that button down there on the slide, and that will help you connect with your phone. So yeah, if you're having any technical difficulties, try out the steps on this webinar, and you should be good to go. But if you are having technical issues that you are having difficulties resolving on your own, you can send a message to me, the host, and I will try to help you out. Note that the chat is closed today, and we will be using the Q&A to submit questions. So please navigate to that Q&A panel that you see in Zoom and use that to submit your questions for today's webinar. Also, just want to let everybody know that we are recording this and we will post this at a later date. Okay, with that, I'm going to hand it over to Yao, who is going to introduce our presenter today.
Julia, it's my honor today to introduce Dane Decoyet. Dane is well known from his research many years ago. Which he did when he was a graduate student at University of Washington, where he really sort of opened the field of understanding the inhomogeneity and these hybrid perovskites and how different grains and these sort of things behave and have different properties. And so that really opened all our eyes to how these materials really sort of work from a inhomogeneity perspective. After his graduate career at University of Washington, he was a postdoc at MIT, after which he joined MIT Lincoln Laboratory, also, of course, in Massachusetts, was technical staff there for a few years, and then decided to start a company, Optigon, for which he is now the chief scientific officer, and Optigon recently joined the US MAP consortium, and so this is why we're getting Dane's insight into these materials and devices in this webinar. So thanks very much.
Then I will share my screen. Here we go. Perfect. Okay, hopefully everyone can see this.
It looks great.
Okay, great. Yeah, thanks, Yao, for the introduction, and really excited to be here. Excited to work with the US MAP team and also share a little bit more about what we've been working on at Optigon. So first, I want to give a little bit of an outline of what I'll be talking about today. First, introducing the team, the solar landscape, and where inspection metrology tools fit into PV manufacturing and research and development. Give a little bit of a background on perovskite characterization and sort of the lens that we viewed it through. Our mission to accelerate perovskite research, development, and deployment. Some examples of how we've collected data from tools that we've developed and also done device predictions, and then future directions of the company. So this will sort of be bookmarking throughout the presentation, and I'll come back to this sort of outline just to let everyone know where we're at as we go through. So first, introducing the team. We actually spun out of MIT in 2021, and we were applying for grants right then, and we got our first grant. It started in 2022. And that enabled us to move into Greentown Labs. This is a really amazing space in Somerville, Massachusetts. It's actually the largest clean tech incubator in North America, with over 200 member companies and about 50 that have lab space. So we have office and lab space there, and we share a lot of equipment. So things such as machine shop, electronic shop, and that's all shared in different startups. We recently launched our first commercial product. We've had our first revenues through measurement as service, and then also just highlighting we have 2 patents licensed from MIT on technology we've been developing. Normally, we would have Anthony joining for a lot of the introduction and what we're working on. He's our CEO. We met in the MIT Grid Edge program. Anthony is our mechanical engineer, and he's worked previously at ASML and has a really great expertise in building state-of-the-art semiconductor equipment. Also, Brandon Motes, who's our Chief Technology Officer, who has experience working at CERN, doing FPGA programming there, and also Johns Hopkins APL. So really excited to have the founding team working with them. And our ultimate goal has been to build smarter measurement tools for clean energy materials. And when I say smarter, I mostly mean tools that are compatible with sort of the data rates and number of samples and manufacturing speeds that are needed to optimize materials these days. So I'll be talking a lot about that today. And let's see if this, perfect. Okay, before jumping into Optigon and exactly what we're doing, I wanted to place a broader context of where we fit into PV. So I think many people probably on this call were at the SATO SIPS peer review meeting a few months ago. And, you know, as I was listening to the presentations, I was sort of noting a lot of, you know, the PV landscape's constantly changing. And so keeping up on numbers is always really interesting, exciting to do. So I wanted to share some of the highlights that I found from peer review. A lot of these graphs can be found also in some of that slide deck, but also generating some of my own slides as well here. So just highlighting this last year, we had about globally 440 gigawatts DC solar installed. That's really exciting, you know, huge year-on-year growth. Also looking into projections of how much solar is going to be installed in subsequent years, shown on this graph. We're continuing to expand. We recently have actually reached about 1.6 terawatts DC globally. And I think there was a huge celebration in the PV community when we got over 1 terawatt, because that means we're starting to become a significant fraction of total energy production in the world. And highlighting just what the future is going to look like. On the right is a paper in Science by Nancy Heigl and a lot of the leaders in the field, showing that, you know, electricity demand by solar PV could be all the way, let's say, globally, anywhere from 45 upwards to 70% by the year 2050. So huge amount of solar coming online, continued expansion, and really thinking about what do we also need to meet climate targets as well. Interesting that that's not working. Okay. So one of the key things, you know, a big question is, how has the Inflation Reduction Act impacted how much PV installations we got? This is just in the US, but shown here is sort of the post-Inflation Reduction Act, the amount of the kind of a big increase in the amount of PV installations. But still, through planned and projected, we're not really meeting what we need for climate targets in order to decarbonize the grid by 2035. So that's from the Solar Future Study by the DOE, the decarbonization electrification scenario, where you can see that the green bars are well below what the yellow line is. And that's where we need to be, really. So still a lot of work to do, you know, from a lot of different aspects, the technology, but also the infrastructure, and so on. And, you know, a big question I think that a lot of us have been talking about is sort of, what is the PV capacity globally? How much solar can we actually make? And then how much is sort of being produced? So what's a theoretical capacity of, let's say, polysilicon wafer cells and modules? And then how much is actually being made? And so this graph is highlighting this all the way from polysilicon to wafers to cells to modules, how much total capacity we have. So that's these sort of dotted lines. And then how much is actually being produced are the solid lines. And right now we have a manufacturing capacity between 650 and 750 gigawatts. At the end of 23, the actual PV production was about 400 to 500 gigawatts. But what most analysts are saying and talking with experts at NREL and SATO is that we really need to be at the current global capacity in order to meet climate goals. So this is actually going to take years for production to really catch up to capacity. And there's several complicated reasons why we're not there. But some things just to consider is really like the economic incentive from, let's say, an oversupply. What does that mean? Are they actually being used? Sort of what's the labor that's available, supply chain issues, and then also just thinking about production yields in general along each leg of the supply chain. So one thing's for certain, I think I've clearly communicated that solar is going to be a huge part of our future, upward of 70% of total electricity production in year 2050, where right now it's only 5%. So, one way that we have continued to get solar out there is continually developing and evolving the technology. And this is just an example of the roadmap over the years of how PV modules have changed. And I would say, most people would say that it's inevitable that we'll continue developing PVs. Going from, let's say, really small ingots to a larger ingot size and reducing the amount of kerf loss to having larger geometric fill factors. And a really interesting point where I think most of us on the call are interested is, 2025 and beyond, what is the technology going to look like? There's very clear trends in what's happening in silicon, going from, let's say, a PERC geometry to heterojunction geometry or TOPCon, and maybe ultimately to interdigitated back contact, the IBC. But we're all fairly certain that we're not just going to stop there. PV development is not going to just stop at those architectures. So we're moving beyond that to continue reducing costs, to continue getting more solar out there to meet the climate targets that we've projected. And so that's going to look like some type of 2-terminal, 4-terminal tandems, as well as multi-junction cells where we're stacking multiple absorber layers on top of each other to get to efficiencies upwards of 40 to 60%. So this is really an exciting direction, and I think something that all of us are excited to be a part of and contribute to, just to continue reducing the cost of solar. So I want to talk a bit about where inspection and metrology fits into the PV landscape. First, talking about just how much inspection costs in a current module these days. So through some nice reports by Brittany Smith and Mike Woodhouse at NREL, you can actually look at the cost breakdown of a monocrystalline PERC cell and look at all the different steps and how much each of them cost to the total cost per watt. And so if we notice that there's a few areas where we see inspection, this is just for cells, not necessarily modules. There's a separate chart for modules. But one of the things that we can just add up these costs and then sort of scale to the amount of installed solar in 1 year. And although this does seem small, just looking at relative things such as screen printing silver or the aluminum paste, it still amounts to over a $3 billion a year spent on quality control and inspection. And that's actually fairly small. And I think, one of the things I want to communicate is that it's likely we could make even further improvements in PV manufacturing by spending even more in this space, which I'll talk about in the next slides. So huge opportunity to continue improving inspection tools and the quality of PVs. So one really interesting set of data that wanted to share is when you have, let's say, a mature PV technology, could be silicon, could be CadTel, could you name your material, and then you're building a new plant. Let's say it's a 1 gigawatt plant. Typically, your production yields start extremely low, sometimes as low as 20%. So you're having, up of 80% scrap rate, just wasting materials. It's not meeting specifications. And this can take several years to get to sort of your nameplate capacity of your production facility. So this is actual data points from a plant of a mature PV tech. And the exact causes of this are not always entirely disclosed, but from what I could gather, has a lot to do with deposition equipment, not working within specifications, not being able to have the right quality control in order to get to the performance and stability that you want for your modules. So that's a long period of time. A big question for us is, can we shrink down that time so that when you're bringing any new manufacturing capacity online, that you can do that in a year or less? Is a big question. Also, another thing to highlight, and this was also highlighted in Nancy Heigel's paper, but mostly in this work by Chen et al., is that it takes about 3 years for a lab champion cell to reach, for a production average to reach a lab champion cell. So, for example, at some of the main solar manufacturing companies, you can make on a small scale a lab champion that's, say, 25% or so, but it's going to take about 3 years in order for your average module to reach about that. So that's a long time. And it seems like it should be pretty straightforward because you know exactly how to build it. Now you just need to scale it. But also this is a question of, can we shrink that time so that you can go from a sort of small scale to large scale and have those efficiency gains very quickly. So just highlighting that quality control inspection is really critical in enabling and shortening these timelines so that we can get more high quality solar panels out there. So I want to talk a little bit more about silicon before we jump into perovskite inspection, because I think we have a lot to learn from the silicon industry. So in the beginning, there was a really critical role of inspection tools for understanding silicon. Silicon's really nice in that it has really, really well-described photophysics. And so you can do things such as photoluminescence imaging and do that as a function of light intensity and extract different parameters such as VOC maps, so actual maps of a cell and how the open circuit voltage should change as a function of position. You can also do that for the power conversion efficiency. So this is amazing. You can just take essentially an image with some correct optics and filters, and then have a really good idea of the quality of the material over its entire area. There's also tools, and this is, I'm just showing an example of some of tools that I think the academic community is very aware of, largely industrial members as well, but also work from Ron Sinton in the 80s and developing some of the first wafer lifetime testers. And you could get sort of implied JV curves as well as things such as doping densities. And thousands of these types of tools from Sinton Instruments have been installed worldwide. So just highlighting that IEEE, PVSC, sort of the main entity for PV specialists and research, really focus both on some of the work by Ron and Thorsten Trupke at UNSW, saying that a lot of this technology really led to this substantial and rapid improvements and cost reductions in silicon solar cell technology over the last several decades. So this is interesting to see on this scale, but if you now look in modern manufacturing plans, this is just showing an example of what a module facility looks like. Is that you'll have these larger pieces of equipment that are shown in sort of these green circles that are doing inspection and metrology along the way. So that might be something such as electroluminescence imaging of a module, where you can look at individual wafers and see if they are within specifications or outside specifications, and if you need to scrap those wafers or replace them. And so it's really looking from what was sort of done in a lot of the research and development and these small scale products to now these really large scale metrology products that fit in every manufacturing line and is a critical part of inspection and ensuring quality. So I think we have a lot to learn from this story. And, one big question is these EL images, these PL images, they really correlate very well to silicon device efficiency. One outstanding question is that also true for perovskites? So can PL, can a lot of these tools that have already been developed for silicon just be directly copy pasted for perovskite? And I'm going to talk a little bit of why this is complicated. And I would say that there's not a direct translation. There is some helpful translations, but not a direct translation. And we're going to look at some data that suggests why this is not the case. So Yao had highlighted a little bit of this work that I had done in graduate school at the University of Washington. And this is, we were trying to understand the microstructure of these thin films and their polycrystalline nature, how it impacted the overall quality and performance of devices. And so in typical form, let's say spin coat a perovskite on a glass substrate. This is a top view SEM image of the polycrystalline microstructure. I had built a confocal fluorescence microscope in order to create these really detailed images of what the photoluminescence looks around these grains. These are much higher resolution than sort of the images that we were looking at from, let's say, BT imaging and Thorsten Trupke's work, because we're focusing the laser to a diffraction limited spot size and then scanning it to create a PL image. So what we found was rather surprising, was that there are entire grains that were low photoluminescence. The grain boundaries were dark, suggesting that there were highly defective regions, and that we could actually improve and target these regions in order to further improve performance. So maybe these PL images were providing some information on how ultimately they'd translate to device performance. But I think some of the kind of follow-on studies were suggesting that this is a lot more complicated than we initially thought. So one way to test this is to continue sort of building out the device, adding a transport layer on top of the perovskite. This is exactly what we did. We put PCBM on top of the perovskite and then looked at the changes after adding PCBM. And so this is just highlighting in this sort of box region, when you add PCBM, the photoluminescence intensity goes down a lot. This is due to charge extraction and quenching. And if you look at sort of a line profile of, let's say, just the perovskite without the transport layer versus with it, you can see that a dark grain decreases a smaller percent than, let's say, a bright grain. So you could sort of say that there's a different number of charges being extracted qualitatively in these two regions. So that's interesting because that should suggest that these regions have different device performance. And actually, Giles, and I don't know if he's on the call or anything, had done a lot of follow-up work on this. So actually using photoconductive AFM and correlating maps, photoluminescence with sort of, power conversion efficiency maps. And this is just showing some of the results there, which was showing this anti-correlation between PL and PCE. So this is very different than silicon, is that typically regions that have more emission, longer minority carrier diffusion length, higher performance. And then what we're seeing here is this opposite trend, and it's not a perfect correlation. And so this suggests that a lot of these sort of PL imaging tools that have been developed for silicon may not necessarily directly apply to the way that perovskites behave. So that's a really important thing to note. I don't want to say that PL is not useful or PL imaging is not useful, because there's really clear ways that we can correlate PL behavior to device performance. So in a very recent piece of work, we were looking at surface treatment with hexyl ammonium bromide to form these 3D, 2D architectures. And you could then add a whole transport layer on top of that and take the time resolved photoluminescence to look at the decays. And so actually what we were able to extract was the surface recombination velocity with using specific models, and show that the surface recombination velocity with the surface treatment is orders of magnitude lower than what it was without the treatment. These actually directly translate to improvements in device performance. So you can see in black the control, and then with the surface treatment, large improvements in both the fill factor and open circuit voltage, which is what we'd expect if we're reducing non-radiative recombination at interfaces. So I will, as much as I was kind of saying maybe PL can be a little bit confusing or not intuitive to device performance, there are clear examples where you can use it as a metric to predict and understand device performance. So we use this to understand how to make 25% efficient devices, but we also use this to push it beyond that, outward of 26%, which is work that will be coming out fairly soon as well. So another complication, I've highlighted this complication of trying to understand the meaning of these PL maps and charge extraction and how they relate to power conversion efficiency. There's also a huge processing parameter space. And so, as we're trying to find the ideal set of materials in order to make the most efficient, stable devices, we've really, explored the whole gamut. So this is work that Pepe Marquez recently shared at MRS that I was really interested in, showing that there's been over 3,000 charge transport layers that have been explored, over 4,000 unique combinations of electron and hole transport layers that have been explored. And this is just highlighting, the main ones: Spiro, PDOT, TiO2, PCBM. And each one of these edges are connecting the nodes, and each of those nodes is a different transport layer. So we're really trying to, find out how to make really high quality materials. And it means we have to explore a wide processing parameter space. And so in the lab, this is I'm in grad school and also during postdoc, and I think a lot of people on the call can relate to this, is trying to find, let's say, new passivating agents, new anti-solvents, new additives that can improve the metrics we care about: efficiency, stability. And so, manually sort of trying out all these different things. More recently, there's been groups that have been developing these sort of automated tools, such as Christoph Brabeck's group, who was looking at different anti-solvents for a lot of different perovskite formulations. And so just highlighting again this huge parameter space that we have to explore in order to really find the best sort of permutation for the devices that are going to be deployed. And then once we find something that we think, is going to work out, make hundreds of devices, especially for a lot of the companies out there making hundreds of devices every week. A lot of the device heavy research groups are also doing this, and just collecting a lot of data and trying to understand what makes a good cell, what makes a bad cell, and then is there a way of doing sort of a root cause analysis for if a cell is bad, how do we improve it? So just wanting to highlight here that characterization tools really have this unique lever to understand why a cell's not performing well, what's the root cause, and then how can we target that in order to further make it better. So I'll be talking a lot about that today and what Opticon's been doing. So Opticon's mission to accelerate perovskite RD and research development and deployment. First, want to highlight that, even before we joined USMAP, and maybe before we were even on USMAP's radar, USMAP had these core objectives. And one of them, the third one down, is inline characterization and metrology. I think widely the PV community has recognized that for silicon, CadTel, SIGs, and other materials, that metrology has been essential in not only doing the research, but developing and then deploying and then ensuring quality during production. And so this has really been a core tenet of USMAP. And right now, currently it's Opticon, our team, as well as Tau Science, that's really focused on this. But we're sure that more companies and other research groups can continue to contribute here as well. So what is sort of our approach, and how are we hoping to accelerate perovskite research development deployment? We're sort of focusing on two different areas. One is the research and development, and then the second is manufacturing. So our goals here are really to develop automated characterization for the research setting, and then also to have predictive quality control during production. So being able to measure, at a few tens of milliseconds to keep up with sort of manufacturing speeds of 60 meters per minute or 100 meters per minute for a lot of different processes. So we've kind of find our unique, I would say, niche within where existing commercial tools are, what their measurement speeds are and how many unique properties they're able to measure. We're really focused on multimodal, so trying to collect a holistic picture of how a solar cell is going to perform. And, one big question I think that all of us have maybe always had is like, what can we measure that's going to be indicative of how a solar cell actually performs? What are the key measurements we need to do in order to understand that? And, I think if you talk with a bunch of PV device physicists, they say different things, but I think generally there's a few things that people generally agree on, which is the alpha mu tau product, or alpha mu tau. And I'm just going to very quickly talk about what those are. So alpha is related to absorption within the PV cell. This is our absorption coefficient. It determines the generation rate within the cell, but also at what depth light is absorbed. And then once you create electron and hole pairs, and eventually you want those to reach the electrodes, those are moving within the material at some mobility. Some centimeter per square per volt second, they're moving around. And then you want those carriers to live as long as possible so that you can extract them before that energy is lost as heat in the cell, and that's related to your tau value. So optimizing all of these, you're going to have the best device performance. And I'll just highlight, this paper is great by Jenny Nelson, Uwe Rao, and Thomas Kirschartz, who I would say are some of the most knowledgeable device physicists out there. So recently, Andrea Corvetto has actually taken this a step further. And, I think one of the key questions we have is what material parameters can we measure that relate to ultimate device performance? Starting to develop different types of figure of merits that include the alpha mu tau, but also other parameters. And so in theory, what you could do is you could measure or calculate all these, input into a figure of merit. And if you know the relationship between the figure of merit and what the power conversion efficiency is, all you have to do is measure these, and then you can get a power conversion efficiency. So this is a really panelizing prospect because it suggests that maybe you might not have to complete a full solar cell, is you can just measure these properties, and if you know them with high accuracy, then you'll know how the solar cell is going to perform before you finish it and do electrical contact and everything. So this is sort of the holy grail of metrology or characterization, is having this amount of intuition. And in fact, this recent figure of merit, I think, has a lot of promise. It's actually showing, if you calculate for all these different absorbing materials, where it lies relative to the actual performance. So inputting your alpha mu tau for perovskites and gallium arsenide and seeing where it lies on this plot, you can see it actually, all these different materials lie pretty close to this line. And this difference is primarily due to unaccounted for, let's say, device physics might be like some sort of series resistance within your contacts or things like that, which you can't necessarily measure in this way. So knowing this, there's really a lot of promise for being able to measure material parameters and then ultimately relate them to device performance. And that's essentially our approach, our goal. So we're developing tools that are multimodal. They can measure sort of holistic properties of a solar cell. We then do analysis of the data in order to extract these meaningful parameters: absorption, recombination rates, carrier mobility, things related to disorder, and then ultimately are trying to predict the performance. So device predictions. So right now we're focusing on transmission related to, that's your alpha metric, spectral resolve PL, which is related to your tau, and then time resolve, which is related to tau and mobility as well, if you're interfacing it with transport layers. So we've actually went ahead and have made a product actually focused on these measurements in particular. And I just want to highlight some of the, I think, unique expertise that we have is all the way from optics to electrical engineering to mechanical design and construction. So we've custom made parts for both excitation and detection for these different measurements and ensuring really high signal to noise. We've also designed our own custom boards for controlling a lot of the hardware, motors and neutral density filters and shutters and things. And then also, how do we integrate all these components to actually make a tool that's going to be able to measure all these in a really user-friendly way? So this is the tool that we ended up building, and I will say this came with a ton of input from research, academic groups, companies, and we're really thankful to a lot of the input that we've gotten over the last year or so in putting this together. So we actually launched this tool recently at Spring MRS. This was just a few weeks ago, and this is Brandon and Anthony at our exhibit booth in the exhibit hall. And so this tool is called Opticon Prism. It has currently 3 measurements: spectral resolved PL, time resolved PL, transmission. These are some of the specifications. I'm not going to get into detail at all about those, but I am excited to show you a video of the tool in operation. So I just want to highlight some of the things we're focusing on is really speed, automation, multiple measurements, and all that's integrated into a database and analysis platform. So the goal is that this generates entirely new types of data sets where you can do root cause analysis along each step of device fabrication. So I'm going to talk through this video as it's going through. So here we have Brandon loading a sample tray. These are just fluorescent microscope slides that are sort of calibration samples. He clicked on image. The samples went to the back of the tool, took an image of all the samples, and now you can see them here. On this screen, this is a live update of the spectral resolved PL as Brandon's clicking on different samples. If he goes to time resolved PL, now it's showing the time resolved luminescence. You can click on any part of the sample. These are just different TRPL decays coming in with different dynamics. And then also can move to transmission and do those as well. So also at the bottom of this, you can see that all the acquisition parameters can be tuned in real time. These also can be automatically optimized based on sample specific properties. And so this is really to make this as seamless as possible. These are standard measurements that everyone's taking already. One thing that is, I think, important is also have this fully automated. And so you can actually place different grids on each sample. So these are, let's say a grid of 3 in this sort of line. Maybe those align with specific device pixels. Or you can also do mapping of an area. So since this is a 2D stage, in addition to collecting single points in different areas, you can create also collect maps in different areas as well. And each of those points is going to have time resolved PL, spectral resolved PL, and transmission. And then this is just a view of what, as data is coming in and being able to sort of toggle through it as it's being collected. Ooh, okay. So that's our benchtop tool. And I'll talk a little bit more about what that's enabled for not only research projects that we've been collaborating, but other research groups. We've also developed a roll-to-roll tool. And this is just an example of it being installed at the Washington Clean Energy test beds in an industrial scale FOAM technology roll-to-roll printer. So I think it's kind of fun to go through these videos. So we'll quickly go through these. This is the roll-to-roll coder. This is the slot die head where the perovskite is actually being deposited. That then goes through this multi-pass oven. And at the end of the oven is where the perovskite's been annealed and where we're taking measurements. So you can see this is that probe head that was also in the benchtop tool that's been put on the roll tool. And then this is being wound further down here. This is actually at 1 meter per minute. So at a fairly slow rate, just to demonstrate that, the tool's working and we can collect data in real time. This is actually the data coming in live stream on an older version of the UI. We actually pushed the measurements up to 60 meters per minute. So you can now see the web coming through pretty fast and the perovskite material coming through. And then also being rewound here. And so, that's a pretty fast speed. And then data coming in live stream as well. Just to give a perspective, most, let's say, inline inspection tools for silicon operate maybe at a few thousand wafers per hour. We're able to measure about 20,000 M6 wafers per hour. So very, very fast speed. And then this is just highlighting, again, this is an older UI just for demonstrating data coming in real time, which is very exciting. So I just want to summarize the Optigon hardware that we've built so far, both the benchtop tool and the rolled roll. So on the benchtop tool, we've actually measured over 300 samples from various collaborators, companies, academic groups, and collected over 35,000 unique spectra and decay traces. A lot of this has actually been correlated with actual device performance. So we believe it's one of the largest data sets that's been generated to test and train different material and device models. So that's very exciting to have access to this data. On the roll-to-roll, we slot die coated 25 meters of perovskite film at speeds anywhere from 1 meter per minute to 60 meters per minute. As I was saying, that's equivalent to over 20,000 M6 silicon wafers per hour. Just in this that short visit to the Washington Clean Energy test beds, we collected over 20,000 data points, about 7 gigabytes of data, and all the acquisition times were 100 milliseconds. So really pushing down what's capable with these types of tools. And just to highlight, we actually changed some of the processing parameters on the slot die coder, so the slot die pumping rate. And we can actually see those show up in some of the measurements that we collected, specifically the PL spectra. There were clear trends as we changed the slot die pumping rate, where in other measurements, such as time resolved PL, we didn't see much changes. So this is just highlighting the need for multimodal measurements so that you can get a holistic picture of how the device or how the material is changing as you change process conditions. So I want to, in the last bit, highlight some of examples of how we've gone about analyzing this data and doing device predictions, because now everyone's probably like, oh, you've collected a lot of data, but what are you going to do with it? And so that's been a really huge effort for us too, is can we analyze this data and predict device performance? So just highlighting, we're really building off on, I would say, a decade of research in perovskites. Looking at nanoscale characterization, trying to understand what's happening in each of these grains, how carriers recombine in each of these grains, how they transport across grain boundaries and within grains, how does the effect of passivation and transport layers impact those features as well. Doing a lot of different work on surface passivation. So when you treat the sample with different materials or add additives, how does that change the properties and how do we quantify those and ultimately relate them to device performance, as I was showing in that recent Nature Energy paper. Also have really done a lot of modeling work trying to understand the different ways to analyze this type of data and relate sort of defects and recombination to emission efficiencies and photoluminescence. And then ultimately doing a lot of device simulations as well. So anywhere from detailed balance simulations with non-idealities, such as non-radiative recombination, to taking into consideration photon recycling and different transport properties. So I don't want to get into a lot of detail here, but I'm just highlighting that we've been thinking a lot about how to analyze this data and have a lot of work over the years that we're building on in order to do that. So I just want to highlight very quickly a few case scenarios where we're sort of using two different approaches to look at this data. The first approach is using essentially a first principles physics-based models to extract meaningful parameters from the data. The second approach will be a ML AI-driven approach. So I think maybe some people are familiar with analyzing photoluminescence spectra, but this is some work that I'll just point to where you can fit a full photoluminescence spectra by using the generalized Planck law. And these are the different components of it. One of the main things that I'll highlight is you can understand a lot about the band edge behavior, the absorptivity function from analyzing a full PL spectra. So things such as Urbach energy and disorder, as well as band gap fluctuations through this. And I actually did this on a perovskite sample that had been tractylphosphine oxide treated, and showing that you can quantify what sort of implied voltages are coming from the cell. So that's a direct link to device performance. And then this is just highlighting, and not to get again too much into the weeds here, but you can also look at time-resolved PL decay traces and use kinetic models that take into account drift, diffusion, trapping, radiative recombination, and look at these as a function of intensity to sort of globally constrain fitting some of the parameters. And this is just an example of globally fitting time-resolved photoluminescence decays to extract things such as the defect-related non-radiative recombination lifetime. And then doing a full, error analysis of what are the confidence intervals, how well did we constrain the parameters. These are all things that we're thinking about and applying to how we're analyzing the data collected with these tools. So this is a summary of how we're extracting different metrics from this data. So we've actually written over 4,000 lines of analysis code. This will be included in an analysis package where we're taking the photoluminescence spectra, the time-resolved PL transmission, and we're extracting things such as the implied voltage, the quasi-Fermi level splitting, photoluminescence quantum efficiency, charge carrier lifetime, surface and interfacial recombination velocities when you're interfaced with material, diffusion coefficient length, the list goes on. And then ultimately, we're feeding those into device models that we've previously developed and are continuing to develop to predict power conversion efficiency, fill factor, short circuit current, open circuit voltage. So I said that we were doing that. Now I want to show you some data where, I think we're really excited about what we've been able to achieve with this so far. So first of all, I just want to thank Amy Lukes and the NREL team, Joe and Axel Palmstrom for providing us some devices to really test doing these measurements. So we were given 3 different batches of half-complete devices. And when these were completed, they ranged from 10% to 17% power conversion efficiency. We didn't know that at the time, but we took measurements on all these samples and then fed them into our device models to predict what the performance was going to be on these half-complete devices. This is showing the results. So we have a plot of current density, voltage, fill factor, and power conversion efficiency. The P is predicted by us, Optagon. M is measured at NREL, the full complete devices on the sister samples. And you can see, based on the measurements and the analysis, that we're getting pretty good predictions for what was actually achieved in the devices. I think one, exciting thing is that we're able to differentiate what's going to be a 10% device versus what's going to be a 17% device, and somewhere in between. I'll say this is, we first started applying these. I'm just curious about how this was going to work, and then actually getting some fairly good results with pretty good prediction accuracy. So we continue to refine and improve these, and the accuracies have also continued to improve along with that. So just highlighting some of these results and the capabilities. We're currently putting this together in a paper that we'll hopefully submit fairly soon. So that's the approach 1. There's also the second approach, which I think maybe a lot of you were thinking about, is this is a huge set of data. why don't we train some machine learning or AI models? And we've worked a lot with Ricky Zhang at MIT and Vladimir Bulovich's group in order to really prove out that this is another option for how we can predict performance. So just highlighting sort of a schematic of training methodology. Ricky and some of members from Munji Blendy's group had fabricated over 200 devices. They came over to Optagon at Greentown, and we measured about 2,500 unique spectra and decay traces. Those were used as inputs, vectorized and put into a neural network training model that was used to predict the performance of the cell. And that was compared to a loss function where we actually took the measured ground truth of the JV curves compared to the predicted output. And then this is continually refined and improved in order to minimize the loss function. So with that, I wish I could share a lot of these results. Ricky should be submitting this paper pretty soon and kind of just have this table to highlight some of it, just because I guess not wanting to share too much here, but highlighting that this approach also led to about 90% prediction accuracies. And more recently, with improvements in the model development, are actually above 95%. So this is, I would say, a bit surprising on how well this is working, just considering all the different types of defects that can be in a device. And with these, 3 measures really capture everything. But at least on these sets of samples and this specific data set, it's working very well. So that's exciting, I think, for any device group or any company that's looking at trying to have good metrics for device performance throughout. So I'm wrapping up here, and I definitely want to leave time for questions. I just want to highlight this is really just the beginning of what the capabilities are. We've built out a whole database for storing all this data. So this not only stores all the measurement and metadata, but you can input specifics to the samples about processing conditions, which layers, what types of layers, concentrations. You can see sort of the stack here and highlighting which layer was deposited and what the measurements specifically correlated with that. And I think this is exciting because you can imagine not only using this for PCE optimization, but also thinking about stability. And a lot of groups are starting to look at this. For example, Hugh Hillhouse's group has done a lot of work on this, on starting to use multimodal tools to predict stability. So training models that can, very early on predict what the stability of a device is before you've even completed it. And that's a really exciting direction that this could take too. So really view it as an enabling technology. So the future of a solar production facility, I think this is kind of our big vision, is really to have these rapid non-contact inspection at each step of manufacturing. There could be live feedback of process steps that would tell you whether this is a go or no-go evaluation, sort of a thresholding. The ability to control process parameters and correct for drifting processes in real time. And also sort of have a self-optimizing manufacturing line. And I'll just highlight that we were recently awarded SBIR phase 2 to do a lot of this effort, and so are funded for the next few years to continue pushing this direction. Also, I'll just say that we're not the only ones thinking about this. In the EU, Platform Zero has a huge effort, over a $10 million effort that's focused on doing sort of self-optimizing labs and minimizing defects in PV manufacturing. So future efforts, just really excited to work with any potential customers, collaborators, anyone that's excited about the tools as well and working on them in their workflow. We're continuing to improve the tools so that they work well for perovskite tandems. And we're adding new measurement capabilities such as Raman, thickness measurements, in the future X-rays as well to increase the density of the data, and then also improving measurement speeds and capabilities. With that, I'll thank you. I really want to thank a lot of the contributors that helped out with code development, Kieran Stoddart, technical advisor, James Motes, Blake Nelson, collaborators, a lot of them on the call, Joe Barry and Amy Lukes for helping provide samples, and then Vladimir and Antonio, who have come by Greentown to, test samples and also provide feedback. And we really wouldn't exist without DOE and SATO. So just really grateful for public support and getting money from the government to really push this forward. If you're curious about us, we recently had an article come out a few days ago in MIT News that gives a little bit more background on what we're focusing on in addition to PV. So with that, I'll end and take any questions, and just this is some of our capabilities. And if you're interested in a product or demo or other capabilities, please contact us. Thank you.
Awesome. Well, we've got just a little bit of time left for questions. So if you have them, put them in the chat. We've got a couple. You know, the one is it possible to use time resolved PL techniques for industrial characterization? I think you've addressed that already. So we'll move on to this question about the models. You know, they're clearly quite good. And the question was essentially whether or not you're able to distinguish essentially the source of the loss in the context of some of the analytic models. Presumably in the black box of the ML, the answer is no, but and I recognize right there that's also kind of ongoing work that we'll hopefully see soon. But yeah, do you guys have any thoughts about that? Can you distinguish, you know, in the context of a half stack between something that's really happening at the surface versus something that's happening at the buried interface?
Definitely. So I would say from that first approach using the physics-based models, one of the ways we've tried to get at root cause is by having measurements along each deposition step. And so that's once you deposit the perovskite and then you're probing a lot of what that back interface is, and then do the same set of measurements, of course, when you deposit the top transport layer. A lot of groups have focused on this, and this is pretty good at isolating. You can also do measurements on either side, you know, so sort of switch the sample around, and that actually constrains what interface and what sort of defects are dominating behavior. So that's a big part of the modeling as well. In terms of the second approach, actually, I think there's more, I would say, interpretability than a lot would think. I think with sort of a lot of the Shapley importance ranking, where you can sort of look at the features and then rank what's impacting most, that allows you to isolate a bit more of what parameters are most contributing to, let's say, a change in fill factor. And so let's say if it's an interfacial recombination velocity term, then you can start looking at that. So there is a good amount of interpretability there. But I would say it's not the same as the physics-based model. And I think that's something that things like Bayesian inference will be able to help out more with.
I mean, so in that context, just to kind of build on that last answer, I mean, but you guys are using, I mean, a range of models, but you aren't explicitly, say, going after some explainable AI-based kind of approach in that context. Is that accurate or fair reflection, or can you say?
Yeah, so it depends a lot what the inputs are. And so if we're using, so I guess the way we break it down is you have the data, you featurize the data, and either you can use some sort of starting physics-based model to featurize it, which might be, let's say, photoless quantum efficiency. That's featurizing the PL spectra into one single scale quantity. You also don't have to do that. You could featurize it in a way that you're just saying, I'm just going to take the onset of the PL spectra, or like the full width half max, which is not as related to actual physics of it.
Yeah.
So there's different ways of training the model with different features that I think give you.
So you're still kind of exploring that kind of assessment, right?
Yeah.
Well, and I guess one of the other questions that we had in the chat, and again, I guess we're running super short on time at the moment, but is the question about whether or not you seem to be essentially overestimating the performance, right? So it lines up pretty well statistically, but it seems to be a little bit of an overestimate. Do you have any kind of thoughts about that as kind of you're moving forward?
Yeah, definitely. So I would say at least for the work that we're doing with your team, a lot of it has to do with just looking at the half stack, I think. And so we're not taking into consideration too much of the non-relay recombination that happens when you introduce that next layer. And so especially in the open circuit voltage, we overestimate because we assume that there's no additional non-relay recombination when you add that layer. But actually, we've done other work where once you add that layer and you take into account, then they kind of equalize. But a lot of these models are sort of maximum predictions based on, you know, quantifying these losses. And so there's other imperfections that are, of course, going to impact performance, like things that we're not considering, like shunt paths and pinholes and things like that.
Cool. Well, given the time, I think we'll have to basically call it at that. But Dane, really enjoyed it, and I'm sure we'll be engaged more with you guys as we kind of move forward. It's been a great collaboration for us so far, and look forward to more of the same. All right, with that, thank everybody, and we'll see you next time.
Thank you.
Dane, great seminar.
Thank you.